For today's tutorial, we want to derive the Einstein's mass energy equation, where we have E being equal to mc². From the definition of work done is equal to force times distance, and in physics, work is equivalent to energy. This means energy is also equal to force times distance. Change in energy here will lead to change in distance. Multiplying the force. Integrate this expression. We are going to have that E equal to the integral of force with respect to S. And we know that force is equal to change in momentum, which is mass times velocity, with respect to change in time, where the momentum in this case is equal to the product of the mass and velocity. So from here, this particular differentiation here, we need to use product rule. Differentiating this mass and velocity, you have this to be equal to, you have your force to now be equal to mass du dt plus velocity vm over dt. From the concept of product rule, we are differentiating two functions multiplying each other. It will be keep the first function, differentiate the second one, then keep the second function and differentiate the first one. Arrive at this place. Let's note this as our equation 2. Why we call this equation 1. So now if we are to put 2 in 1 now, to put this equation 2 here rather, we are going to be having what? E should be equals to the integral of, in place of force now we are going to substitute this whole thing here, mass du over dt plus v dm over dt with respect to the distance traveled. Okay, so here, if we are to use this change in distance here to open this bracket, because there is a way we could substitute if we do that. So we'll have it to be the integral of mass times the velocity times change in s over dt plus velocity times change in mass times change in s over change in t. And we know that in physics, change in s over change in t is velocity. That is change in distance with respect to time. So in place of all of this, we put velocity. We put velocity here. You have it to be the integral of mass times velocity, change in velocity, plus velocity squared, change in mass. Okay, so this are energy being equal to all of this. So let's name this equation 3. This becomes our equation 3. And on reaching here, from the concept of relativity in physics, we know that the relativistic mass m is equal to the absolute mass all over square root of 1 minus the velocity all squared all over the constant speed of light all squared. So from here, this same thing can also be written as what? It can be written as the m naught all over, or rather the m naught multiplying 1 minus v squared over c squared raised to the power of minus 1 over 2, because the square root in this denominator is same thing as power half. The inverse of it, same thing as minus. From the knowledge of indices, this is cleared, so it becomes mass multiplying the whole of this. So from here, if we are to differentiate this mass, we are going to have, let's move to the next page and do that. If we are to differentiate the formula, m equals to m naught bracket 1 minus v squared all over c squared minus 1 over 2. If we are to differentiate the mass here with respect to the velocity, since this is a constant, we are going to be having it as the m, that is change in mass over change in velocity. We are differentiating mass with respect to velocity, so change in mass with respect to velocity will be equals to this minus 1 over 2, okay, bracket 1 minus v squared over c squared bracket minus 3 over 2 bracket minus 2v over c squared. When you differentiate this particular equation properly, you are sure to get this. So from here, it is clear that 2 cancel 2 here, so you are left with m naught multiplying the velocity all over speed of light all squared bracket. Now you split this constant speed of light squared here, this is what we factor out here, and the velocity here is it, minus multiply minus become plus, so you have the velocity here, your mass here, and your constant here. So now this particular expression is what is left. You are going to split it into 2. Splitting it into 2, you have it to be 1 minus velocity squared over speed of light squared raised to the power negative half multiplying 1 minus velocity squared over speed of light squared raised to the power negative 1. That means if you multiply these two things, you are going to get this back. So from here, we can rewrite this as v over c squared multiplying, the inverse of this means 1 over everything, so this will now multiply this, 1 minus v squared over c squared, everything multiplying Now the m naught here, the inverse here also means 1 all over all of this, which means you have to have 1 all over all of this raised to the power of half, which means square root. That means you have to be having 1 over square root of 1 minus v squared over c squared. So now from here, the mass m naught multiplying 1 gives us m naught. So you have this equation as being this. Okay, so from here, since we said earlier that the relativistic mass is equal to the whole of this, and we now have it here. So in place of this, we are going to be putting the relativistic mass. So you have all of this multiplying the relativistic mass m, and here simplifying it, you will have this. Okay, now it's clear that c squared cancels c squared here, right? So we are left with mass times velocity all over the speed of light squared minus velocity squared. Remember, the whole of this is the derivative of mass with respect to velocity. So you bring it down. The derivative of mass with respect to the velocity now is equals to product of the mass and velocity all over the speed of light all squared minus the velocity all squared, right? So from here, if we are to cross multiply this particular equation, cross multiply, we are going to be having c squared dm minus v squared dm to be equal to what? mv dv, right? Moving this term to the right hand side, you now have your c squared dm to be equal to mv dv plus v squared dm. So let's call this our equation 4. Let's call this our equation 4. So now if we are to put equation 4 now into equation 3, the equation 3 that we had earlier, the equation 3, since mv dv plus v squared dm in this case is equal to c squared dm, that means if we substitute that into here, we are going to be having that our energy now is equal to the integral of what? C squared dm. Okay, and the c squared here is a constant, the speed of light. So whenever you integrate constant from the concept of integration, you have the constant back, then you integrate the remaining. So the integral of change in m, change will cancel integration, so you now have it to be what? To be equals to mc squared mc. Now have therefore that your therefore your e equals to mc squared. We have successfully proven